All right, so today we're going to start Chapter 2. Chapter 2 is going to move us into derivatives. So I know a number of you guys have had some amount of calculus in your past, so that word rings bells to you. So today we're going to be taking a look at the derivative and the tangent problem. And we have actually started taking a look at this back in section 1.1 when we talked about secant lines and tangent lines. So let me just remind you what we looked at before on that. We had taken a look at these graphs, and this is an arbitrary shape that I'm drawing, but I'll make sure it's the same shape on both graphs. So our graphs can look something like this. And I can copy paste, so I'm going to. So when we're looking at secant lines, we're looking at taking a point C, and it doesn't really matter where we put C, and a point that's a little bit away, and I'm going to make it a lot of it away because it's easier to draw, but this point is C plus H, so the distance between them is H, they're just a distance away, and we take the ordered, or the 2 points that correspond to them, and we find a line between them. So this point is f of C plus H, and this point right here is f of C, and we draw the line between, something like that anyway. And we find the slope of this line. Do you remember drawing a picture something like this before? Yeah? Okay. What happens when we look at the tangent line is we let that distance h between them minimize. We let it go to 0. So we're taking a limit, right? We've talked about limits back in Chapter 1 as that distance or that space between approaches 0. So we take that same point C, and now that I didn't copy and paste that, it's not going to be quite the same, but we're going to get close. So this is f of C. And we minimize that distance. So we take the point getting closer. So where was my point before? It was about here. And we drew the line that connected them, something like that. And then we let the point get really closer than it was before. And we draw the line again, and it looks something like this. And we let the point get even closer yet. And we draw here, and we draw the line again. And it looks something like this. And so that space h goes to nothing in between, and that is approaching what's called a tangent line at C. So the slope down here of the secant line is the change in the y's, so f of C plus h minus f of C, divided by the change in the x's, which is C plus h for one of them and C for the other. And when you simplify the denominator, the c's cancel out because you have C minus C, so you end up with h in the denominator. Okay, so this is the slope of the secant line. What happens when we move into tangent lines is we take the limit of this quantity as h goes to 0. All right, so that's what's actually going to show up on our next screen. This is the definition of the slope of the tangent line. If f is defined on an open interval containing C, okay, so defined means that we don't have any gaps or holes or asymptotes. And the limit, as h goes to 0, of f of C plus h minus f of C over h equals m, that limit exists. Then the line passing through that point with the slope m is the tangent line to the graph of f at the point C f of C. The slope of the tangent line to the graph of f at the point C f of C is also called the slope of the graph. At f at x equals C. Okay, so all this is telling you is that we're taking the limit of that slope of the secant line, and it has a name. It's called the slope of the tangent line when we take that limit. It's also called the slope of the graph. It's going to be called a couple other things by the time we're all said and done. It's going to be called the slope of the curve, and it's going to be called the derivative. So all of those phrases are interchangeable. And we're going to do this limiting process. So this is a very algebraic section. So if algebra is not top of your list, you may not like what we're doing here. But if you felt like you're good with your algebra skills, you might. So we're going to be doing a lot of algebra in this lesson. And I know some of you are like, well, can I do a shortcut? And others of you are like, shortcut, what is that all about? Okay, so we're going to do shortcuts, but that's going to happen in section 2.2. All right, so for section 2.1, if you know anything about shortcuts, you can use that in your mind to do a check step for yourself. But you can't use them yet, because we want to make sure that we understand the algebra that's behind those shortcuts. So here's our first example. This one says we're going to find the slope of the tangent line of the graph of the function at the given point. So here's what we're going to be doing. We're going to be finding the limit as h goes to 0, and I'm going to write it several times. This function's called g, so we'll call it g, of g of x plus h minus g of x over h. Sorry, that's running into it a little bit. I'll shift it down. This is what we're going to find. And at the end, we're going to plug in x equal 1. Could we plug in x equals 1 right now? We could, but we're just going to wait till the end because that way when we aren't given a specific x value, we still have the same process in place. We don't have to recreate the wheel. So what does this look like? Well, it means that we're going to take this function right here, and we're going to put it right there, because the function's name is g of x. G of x is 6 minus x squared. So I've got the limit as h goes to 0. We'll fill in the first part in a minute, but the g of x is 6 minus x squared, and h is just h. So those pieces you can plug in automatically without doing any work at all. They just go in straight away, right? The 6 minus x squared in this case, the h stays the same in the denominator. The first piece, however, we need to replace the x with x plus h. So this is our function. It has a 6 in it. I'll put it in brackets to remind us that we're separating it out from the other piece. And where the x is, we want it now to say x plus h. I'm going to show you one other way to do this too before we're all said and done. Okay, so where the x is, we replace it with x plus h. We need to simplify this expression. So, limit as h goes to 0. The x plus h, please do not be tempted to do x squared plus h squared. It is not. 3 of you are going to do it. I don't know which 3 of you, but 3 of you are going to do it on some homework problem, and I'm going to be like, oh no, I failed them. It is not x plus h squared, or x plus h squared is not x squared plus h squared. When we do x plus h squared, it means that we have to do x plus h times x plus h, right? Should be ringing bells even if you were tempted to do it to begin with. It means you have to FOIL. So you have to do x squared, your first term. Your outer term is xh. Your inner term is xh, and your last term is h squared. And so it becomes x squared plus 2xh plus h squared. It's from algebra. Told you there's going to be a lot of algebra we're doing today. Okay? So in the place right now, I've got the 6 of the x plus h squared. I now have x squared plus 2xh plus h squared. And then I have minus. If you want to go ahead and distribute this through, you can. I'm just going to leave it like it is because there's something that really nice that's going to happen, and I'd like to be able to see it a little bit easier with it written this way over h. Okay, so your choice if you want to distribute the negative, it doesn't matter. You can if you wish. The negative right here, though, now, we are going to distribute that through. So this is the limit as h goes to 0. Every single time we write limit, limit, every single time, okay, until we actually put a 0 in for h. And now I have 6 minus x squared minus 2xh minus h squared, and then minus, and I have the 6 minus x squared over here. Okay, everything in this second piece along the way is going to cancel with something in the first piece. So do you see how we've got a 6 right here at the very beginning? We've got a 6 right here as well, and there's a negative. So this 6 is going to cancel with this 6. This negative x squared that's happening in the into the parenthesis has a counterpart that's a negative x squared in here. It's it's a negative x squared in the first piece, but because of the negative here in the middle with the negative x squared here, it's going to be a positive x squared. So either you distributed it through or you left it like I did, and it's going to cancel as well. So at this point in the numerator, I have a negative 2xh minus h squared, and in the denominator I have h. Is everybody good to that point? See where all the pieces went or went away, why they went away? Good. At this point, everything in the numerator has an h in it, right? And there's an h in the denominator. And that will happen every single time. So if at this point you get to something where you don't have the h in the denominator being able to cancel out, you've probably made a mistake. You need to go back and find it. So this h should reduce with every h in the denominator one time. It divides each of the h's out. So I still have my limit. I still haven't put h as 0 in. I'm really close though. And now I have negative 2x because the h canceled. And one of these two h's canceled, right? So I have still minus h. And then I don't have a denominator anymore. If you want to write it, you can write it over 1 if you wish. This is what has to happen in order for me to plug 0 in for h. So at this point, when I no longer have an h in the denominator, it's perfectly okay for h to be 0. And I can let it be that. So I have negative 2x, I have minus 0, and this ends up giving me just negative 2x. Is that okay? All right, we are going to put in x is equal to 1 here in a minute, but I want to show you another way to do this that's a completely separate process, okay? So if you liked that process, that's fine, and you can do that, but there is another completely separate way of doing this. I'm going to delete this over here, and I'm going to put it on the other side of the screen so that you can see them in contrast and decide which method you want to use. Okay. The second way of doing this is called the 4-step method. So I'm going to outline what each of the 4 steps are, and I'm going to number them as I go. It's the same thing that we just did. It's just broken down into pieces instead of doing it all at one time. My preference, personally, if I were doing it, I would do the second way I'm going to show you. But the way that I learned it was the first way that I show you, and that is the traditional way it's taught. Okay? So the first step is to find, in our case it's called g, so g of x plus h. Okay? So g of x plus h. All right, so I do 6 minus, that's the x plus h squared portion that I did before. Okay, I take the g of x equation, and I substitute in x plus h for x. All right, so I have my 6 minus, we already went through that this is not x squared plus h squared, it's x squared plus 2xh plus h squared. And when I distribute my negative, I have 6 minus x squared minus 2xh minus h squared. That's step 1, just cleaning up the x plus h that's being squared and so forth in the process. Step 2 is to take that same g of x plus h that I already found and subtract g of x. All right, so what does that look like? Well, I'm going to have to go down to the line below, but it's taking the 6 minus x squared minus 2xh minus h squared, and it's subtracting off the 6 minus x squared. If you compare it back to the other side of my screen, it's the entire numerator. Right? So I did the first part of the numerator, the g of x plus h part right there. And now I'm doing the second part of the numerator, so I have a whole numerator. The whole numerator is step 2. And of course, the beautiful thing about it is that each of those cancel. The 6's cancel, the x squareds cancel, and all I'm left with now is the let me move it down a little bit, the negative 2xh and the minus h squared. So this is the end of step 1. This is the end of step 2. And now we're on to step 3. Step 3 takes the g of x plus h minus the g of x, and it divides it by h. So we take the result of the previous step, negative 2xh minus h squared, and we divide by h. We're just doing a piece of the process at a time. Okay, so again, we get to a point now here where I see all the h's start to collapse, right? Everything in the numerator has an h, the denominator has an h, and I'm able to reduce each of those pieces to giving me negative 2x and minus h. Step 4 is the limit part. So I take the limit as h goes to 0 of what I just got. So I won't write it out, but it's the result, the negative 2x minus h from the previous step. I plug my 0 in for h, and it's just negative 2x. There's a lot of nice things about this way. One of the nice things is that you don't have to keep the limit all the way along, because if you use the method on the left and you leave limit off of any individual step, I'm going to take points off. And the reason I am is because that means that one step is not equal to the next one, right? You're sort of shortcutting something along the way where things are not equal to one another. So that's kind of a nice step here, where I only have to do the limit at the very end. It's also nice on the 4-step method, in my opinion anyway, because I'm just working on one component at a time. I'm not having to remember all the pieces all the time, not just the limit piece, but all the pieces every single time. I don't care which of these you use. It doesn't matter to me. It doesn't matter to the grader. We will have talked about both options, and that person will be able to grade both options. So whichever one you like, that's what we'll do. I'll probably do one more of each of the methods today, just so that you can kind of get a feel for them again. We're not done with this problem yet, but these are the 2 different ways you can get to this point. Once you've gotten to this point, of course, you still have the same answer at the end. The negative 2x is right. So once you get to the end of this point where you find that value, what we're going to do is we're going to evaluate it at x equal 1. Okay? So at the very end, and I have no space, so move it up. At the very end, what you do is you take the x, so this is supposed to be at negative, was it negative 1? No, positive 1, 1, 5, and you evaluate it. So you take this x value. Why are they giving you the number 5? We'll see why they're giving you the number 5 later. It just doesn't affect this problem. They're evaluating at x equal to 1. So at x equal to 1, we have our function value. It was negative 2x. So we have negative 2 times 1. And our value is negative 2. So we're just plugging in x equal to 1 at the end. Negative 2 is our answer. Okay, so we've got a couple more examples, but before we do that, we're going to formally describe the derivative then, and you'll notice it looks a lot like what we already did. The definition of the derivative of function. So the derivative of f at x is called f prime of x. And it's equal to that same expression that we saw before on our previous definition. Limit as h goes to 0 of f of x plus h minus f of x over h, provided the limit exists. For all x for which this limit exists, f prime is a function of x. So in other words, as long as the limit exists, if f is a function, f prime is also going to be a function. When we get to exam 2, I'm just going to tell you right now, you will memorize this. And at that point, it will not be an extra credit bonus problem like it was last time. All right, this is something I will ask you to write down, and you will write it down So if it takes you a while to memorize things, that's your warning right now. We've got several weeks before that's the case, but you will need to have that memorized. Okay, so we're going to do this process again. I'm going to do it this time from the get-go and just use the four-step method, okay? So you'll have an example of four-step method. We have one more in a minute, and I'll use the other limit process that I did as the first step. I'm not going to do both of them every time. But you can choose to use the other one. So if you don't like the four-step method, and I'm about to do the four-step method, just do the other one. And you can check to make sure you got the same thing that I did at the end. All right, so we're going to find the derivative by the limit process. You'll notice that this one looks different than the last one. The last one was actually a polynomial, quadratic specifically, or a parabola. This one's a rational function. So we're going to see sort of a difference on how we operate when the function changes to a different form. All right, so my four-step method, which is the one I'm going to do this time, says the first thing I'm going to do is f of x plus h. So in my function, in place of x, I do x plus h. So I have 1 over x plus h quantity squared, and I do want to simplify the denominator. We've already done x plus h squared, so it will always be x squared plus 2xh plus h squared. So I have that in there. So that's step 1. Step 2 is to take f of x plus h and subtract off f of x. So that's my previous step, f of x plus h. Oops, we'll write it out the way we had it. X squared plus 2xh plus h squared. And we're supposed to subtract off the original function. Now, when I did this as a polynomial, it got prettier, right? It looked nicer. Things collapsed really quickly. It was better looking after step 2 than after step 1. Let me remind you, take a look. Step 2, the result was better than the step 1. Easier anyway, simpler. It's not going to look like that here. And it's not going to look like that because I have two denominators, and they don't match, and I need to consolidate them, which means I need to get a common denominator, right? It's going to get messier in this particular time. It's okay. You guys can handle it. We're going to do x squared on the first one, and we're going to do x squared plus 2xh plus h squared on the second one. You might be asking yourself, well, would it be nicer if I did the limit one? No, it's still going to be messier at step 2, no matter which method you do. However, the denominator, I don't want to distribute that through and multiply that out. That's not going to be a helpful process. So in my denominator here, it really is going to stay in this, factored looking form, x squared plus x times x squared plus 2xh plus h squared. It's going to stay like that. But my first numerator is going to say x squared. I need some space. And my second denominator has a negative right here, and it's going to apply to everything in that new second numerator. So I will have negative x squared, negative 2xh, and negative h squared. Is that okay? Everybody saw where everything went? Yeah? Okay, so there is something that's going to cancel out. What's going to cancel out? Yeah, the x squareds. I've got a positive and a negative x squared on top. So for the sake of space, I'll put it over here to the right-hand side. I just have the negative 2xh. I have the negative h squared, and then my denominator is still x squared, and then x squared plus 2xh plus h squared. So it simplified a tiny bit from where it started, but it didn't actually simplify from step 1, right? It looks messier than step 1 in this particular one. So here's where we are at this point compared to here from step 1. Step 3 is to take the f of x plus h minus f of x, that is step 2, and divide it by h. So I want to take this expression and divide it by h. Dividing it by h is equivalent to simply putting an h in the denominator as a factor. Right? I don't want to write this thing and then put a big division sign and put an h on the bottom. That's going to look horrible. It is equivalent to simply putting an h right here on the denominator part of it. So that's how I'll write it. So I have negative 2xh minus h squared on top. My denominator starts out the same. I have x squared. I have x squared minus plus, 2xh plus h squared. And then I also have an h in the denominator. That's step 3 to start with. Here we are, right? I promised you lots of algebra. I'm delivering lots of algebra, right? Definitely. Okay, but cool. Look at this. See this h that I just threw in the denominator? Just like on the last problem, there's h's that cancel with it in the numerator, right? Yeah, and that does always happen. So on this step, when I put that h in the denominator, the h from each of the pieces individually in the numerator will cancel. So it does clean up on this step again. I have negative 2x now on top, minus h, right? H squared divided by h is h. And my denominator is x squared times x squared plus 2xh plus h squared. So at this point, we no longer have a problem with the h standalone in the denominator because it canceled out with something in the numerator, all the pieces of the numerator, in fact. Why does it matter? Well, because step 4 is letting h equal 0. So in step 4, we take the limit as h goes to 0 of the quantity that remained from step 3, which is negative 2x minus h over x squared times x squared plus 2xh plus h squared. So notice, every h becomes 0. So this piece becomes 0. This piece, because it'll have a 0 in it, will become 0. And this piece becomes 0. Everything I circled is now 0 because h will be 0. So all those circled pieces will disappear when h is 0, leaving me with a negative 2x on top. And I have x squared and another x squared on bottom. So negative 2x on top. I have this piece x squared. I have this piece x squared on bottom. There's no more limit at this point because I put the 0 in for h. I did that process. But notice I've got x on top and an x on bottom. I've got some x squareds. There's a little bit of cleaning up I can do here still, right? So I will reduce one of these x's with one of these x's. So I have negative 2 on top. And then I still have the x here and the x squared here, and x times x squared is x cubed. So I have negative 2 over x cubed. Is that okay? It's a lot of steps. These problems are going to take you a while. Okay? They are doing them with this method. When you get to your exam, you're only going to do one of them like this. There will be one problem where you do this. I see people praising God already. It's amazing. One problem like this on your test. But it's going to be really hard if you don't practice several of the problems like this by hand now, right? It is. It's going to be really challenging. You're just going to be forfeiting those points if you don't do some practice beforehand. All right, let's do another one. I wanted to show you several different types of problems. The first one we did was a polynomial. The second one is a rational function, and this one is a radical. And something we do within this problem is going to feel like something we've done before. So as it happens, and you're like, I feel like we did this before. You did do something like this before. So this one actually has slightly different directions, so just be aware of that. We're actually going to find an equation of a tangent line here, not just stopping at the end at negative 2 over x cubed or stopping at the end over here where we just got negative 2. We're going to do something one step further. So we're going to do all the same processes that we've done on the last two problems, but at the very end, we're going to have an extra step. And then part B says to confirm it with your calculator. So we're just going to graph the answer that we got along with the original equation that we were given so that you can see that it makes sense. Okay? Okay, so I promised that we would do another one with the limit all together piece. So if you don't like that idea and you want to do the four-step method, by all means, you do the four-step method. I'm going to show the limit process completely, and then we'll make sure that we both have the same thing at the end. Okay? So I'm going to write it all out. We want the limit as h approaches 0 of f of x plus h minus f of x over h. If you're doing the four-step method, your first step is to simply do the f of x plus h. All right, so this piece at the end is the f of x piece. So I have the limit as h goes to 0. I have square root of x at the end, and I have h on the bottom, minus square root of x. The first piece is the piece where I replace the x with x plus h. So instead of square root of x, I have square root of x plus h. Okay, is that all right? Okay. You've seen, ignoring the limit part, you've seen stuff like this before, where you have a radical minus something, or something minus a radical, or in this case, two radicals that are subtracted. Do you remember how we eliminated the fact that we had radicals in a portion of the problem? Yeah, we used conjugates, right? So we're going to use conjugates here again. So the conjugate to the x plus h square rooted minus the square root of x would be the same thing, but with a negative sign. So we have a square root of x plus h, and then minus the square root of x on top and on bottom. Oh, minus was in my problem. I was zooming in and zooming out. Thank you. Okay, so this is the screen that I'm seeing right now. So when you see me make a sign mistake, it's because I don't see it on my screen. You'll see this? I have to zoom in, otherwise you're not going to get anything that makes any sense in terms of my handwriting. So please let me know when I miss a sign or something. Yeah. Okay, is that okay? The conjugate, top and bottom, cool. Why? Why do we do the conjugate? Well, we do it because when we multiply a value by its conjugate, we cancel out the middle terms from the FOILing process. The outer terms, x plus h times the square root of x, and the inner terms, the square root of x times the square root of x plus h being negative, they cancel out. So I end up only having to worry about the first two terms multiplied. So the square root of x plus h times the square root of x plus h simply becomes x plus h. And then at the end, the negative square root of x times the positive square root of x simply becomes minus x. That's why I do it every time. But in the denominator, I don't have to distribute. In fact, you really don't want to distribute. You want to leave denominators. Anytime you're working with limit process or the four-step method, you want to leave those denominators in factored form because something's going to cancel out. So right now, I have this in my denominator. Still, limit as h goes to 0 at the beginning. Okay? What do you notice happens on top? You bet. The x's cancel, leaving me with h. So I have a single h on top. I have this h on bottom. What's going to happen? They're going to cancel out. You bet. So this h on top and this h on bottom. And when we say cancel, what we're talking about here is division, right? So when we divide h by h, what do we get? 1. So we don't get 0 on top. We get a 1 on top. And technically, the h in the bottom becomes 1 as well. It's just that when the 1 is multiplied out, it doesn't affect anything. So my numerator is now 1. And my denominator is now simply the x plus h. And I missed my sign again. Plus x. Make sure you caught that because I messed it up. There's a plus right here from the conjugate. Plus, plus, plus. Okay, is that all good? Can I let h equal 0 now? Sure can. It won't zero everything out in the denominator, so I'm good to go. If h is 0, I end up with 1 on top and square root of x plus the square root of x on bottom. Square root of x plus square root of x can simplify to what? 2 square root of x. Now, if the directions had been like they were on the last problem over here, where it just says find the derivative, we'd be done right there. This would be the derivative. And you might be looking at that and saying, do I need to rationalize it? And the answer is no, you don't, because depending on what x is will depend on whether this function's rational or not, right? Not function, but the value. So anytime you have a variable with a radical, it's perfectly fine to leave that in the denominator. You don't have to rationalize it. That's not quite the directions for this problem. The directions for this problem said that we're supposed to be finding the equation of a tangent line. So at this point, we need to go back up and take a look at the point value that we were given. This says x is 1 and y is 1. Okay, so x being 1 means that I will evaluate. This is the derivative, f prime of x. I will evaluate now the derivative at 1. Okay, so that's actually fairly nice. I have 1 over 2 square root of 1. What's the square root of 1? 1. So this actually just gives me the value 1/2. That's a friendly value, right? We're pretty good. What did that tell me? What did the derivative tell me? Well, it tells me the slope. That's what derivatives are. They're slopes. Remember slopes of tangent lines? So this is the slope. And over here is the point. If you have the slope and you have the point, can you create an equation of a line? You can. There's a couple of ways you can do it. The one that you probably will want to use is the one that looks like this. Y minus y1 equals m times x minus x1. Again, from your last algebra course or pre-calc course you took, this is the equation of a line. The m that we just found was 1/2. And the xy ordered pair, which is why they gave you both x and y, was 1, 1. So this is x minus 1 and y minus 1. So this is the 1 and the 1 that they gave you back at the beginning of the problem. You found the slope 1/2, and we will clean this up to write it as y equals. So I have y equals, so this is 1/2 x minus 1/2, and then I'm moving my 1 from the left to the right, so plus 1. So I did 2 steps in 1. I distributed my 1/2s, and I added my 1. So my equation is y equal 1/2 x, and then what's negative 1/2 plus 1? Positive 1/2, yeah. Okay, so this is like the answer to part A. Part B is you confirming with your calculator. So grab your calculator out if you have a graphing calculator. If you do not, I strongly encourage you to get access to one as soon as you can, because there's going to be places all the way along the semester where we're going to be doing things like this. You're going to put in the original equation that was given to us, which is this one, right? Square root of x. And you're going to put in the equation that you just found, which is 1/2 x plus 1/2. You can put them in as fractions or decimals, it doesn't matter. If you want to do 0.5x plus 0.5. In terms of your window really can go from like x equals 0 to x equals 5 if you wish, because that's enough of the screen to see what's going on. And the same thing for your y, 0 to 5 is fine. In case you don't have a calculator with you today, I'll graph what my calculator screen looks like, and that way everybody can see whether there's matches as well. So the screen looks something like this. That's the graph of square root of x. Okay, we're supposed to be looking at the ordered pair 1, 1, like this. And the equation that we created ends up looking something like that. That's reasonable, right? If the graph looked more like this, we should be concerned, yeah? It should hit at 1, 1. Whoops. That's what happens when you tell it to delete. It should hit at the point 1, 1 and be tangent. That means barely touching, or just barely, like sometimes people tell me it looks like it's kissing. It's kissing the graph, right? Or it's bouncing off of the graph at 1, 1. Any questions on that? Okay, the last bit that we have here today, I'll go very quickly. There are some places where derivatives do not exist. Three places specifically. Derivatives or tangent lines, slopes of tangent lines and so forth, do not exist at discontinuities. So discontinuities means we're talking about holes, any holes, or jumps, or actually asymptotes as well, because that would be a break in the graph too. And of course, we're looking at things like this. It's a jump, or we have an asymptote going like that, right? So none of that will work. No derivatives at those points. Sharp turns. Sharp turns, tangent lines don't exist. So this looks like this. And if you can imagine, the reason is because if you were doing a tangent line from the left, it would look like this, right? And if you're doing the tangent line from the right, it looks like this. They don't approach one another, right? At some point, it sharply changes what's happening. And so this particular location where there's a sharp turn doesn't have a tangent line. Therefore, it would not have a derivative. And the last one, which it comes up super rare, it's going to maybe come up one time this entire semester from what I remember, in like a homework problem or a problem I do on the board or something, one time. They're vertical tangent lines. So if you have a graph that's super sharp like this, it's not a great picture, but something like this, this location where the vertical tangent line would happen would mean that it does not actually have a slope there because vertical lines have undefined slope. So our tangent line is not going to have a derivative value at that particular point. Okay, so the last thing that we're going to look at is differentiability for continuity. So if we have a function that is differentiable, differentiable means it has a derivative, then it automatically is continuous. So over here, continuity was not enough. Like this second one, it's continuous. The third one, they're continuous, right? But they still had places where the derivatives didn't exist. However, if you know that the function is differentiable, it has derivatives, you also know that it is continuous. So continuity is a necessary condition for differentiability, but it's not a sufficient condition. It's not enough. But if it's derivatable, that's not right. If it's differentiable, you do have continuity. So I'm going to do one real quick example. And if you don't know how to graph this on your calculator, it's okay. You can come and see me if you have a problem with it, or you can go to the Success Center. They can help you do the graphing for it. This is a really good example of an equation where it's actually continuous the whole time, but it doesn't have all the derivatives that we would like. So I'm going to sketch you the graph so you can see what it looks like, because it's an interesting graph. If you had just the graph of x squared minus 9 without the absolute values, you would know what it would look like. What would it look like? Don't everybody talk at once. X squared minus 9. What's it look like? It's a parabola, right? It's a parabola shifted down 9, right? So I didn't draw this very well. It actually would look something, if it were without the absolute values, it would look something like this. Agreed? Okay, so what happens when you do the absolute value is everything on the bottom has to flip up to the top. So you end up with a graph that looks instead like a parabola on the edges. Whoops. This isn't perfectly symmetric, but it flips up in the middle. The bottom part flips up. And your calculator can graph that for you too. But does that make sense from the perspective of parabolas and absolute values? And where does it flip up? Well, it flips up. Where do you think these points are? What's your guess? Yeah, it's 3 and negative 3. So negative 3 and 3. And the reason it's 3 and negative 3 is because if you put 3 or negative 3 into the x squared minus 9, you get 0. Right? That's the flipping up part. So as you're taking a look at this equation in the graph form, can you see which pieces of it now will and will not have derivatives? Okay, it's continuous everywhere, so that's not a problem. But which of these problems do you see happening? Sharp turns. And you can also see where the sharp turns happen. Where do the sharp turns happen? Plus and minus 3, right? So where in the world is this differentiable? Well, it's differentiable most everywhere. It's just got those two places, each of those individual places that don't work. So it's differentiable on negative infinity to negative 3. That's the first part over here. It's differentiable in between them. So from negative 3 to 3. And then it's differentiable after them from 3 to infinity. So where is it differentiable? Well, what you really are asking yourself is where is it not? Where is it not? And then I find a way to exclude those points. This is interval notation. If interval notation is something you haven't seen in a while, you're not really sure how that works, that's something to get clarified real quick, because I'm going to assume that interval notation is comfortable for you. that you know what I'm doing with it when you use brackets and when you use parentheses. So if it's not, that's okay. It just means you need to ask in the Success Center or come ask me so we can get that clarified. Any questions?
Can you also put like army numbers?
You could, but on WebAssign, it's going to do something like this. It's going to want interval notation for WebAssign. Yeah. All right. Have a great weekend. This homework is now assigned and due in WebAssign before we meet again.